Hello, everyone. I wanted to make a quick video about a project I did yesterday. And also, I wanted to talk about potential ways of extending this project in the future. So, this project was inspired by causal inference and probability theory. I wanted to get at the essence of these subjects by removing all of the mathematical notation and also simply trying to develop the ideas as if I had never taken these courses before. So let me show you what I came up with. All right. So the core idea here is that we are going to develop a dog population. We are effectively going to play God a little bit and pretend as if we are able to create dogs and create a dog population from scratch. So one core idea we have is the idea of a variable. A variable is just a property. And so I'll use these terms interchangeably. Now, if I show these properties, we can see we have several properties we're looking at. Genetics, age, sex, fur color, nutrition, size, tail length, activity level, weight, and collar color. Now, what do these arrows represent? These arrows represent that certain variables, their values are determined by the values of other variables or properties. So for example, size, this property is determined by the values of the genetics property and the age property. Once the genetics and age property have been assigned a value, there is a mechanism that takes this value and determines the value of size. But what about these properties that don't have any arrows pointing at them? Well, these ones are determined by random number generators. So this is how we imagine the world works. We are going to imagine that, you know, as God, we can create dogs this way. We use a random number generator to generate sex, nutrition, genetics, and age. And then we allow these rules to play out. Fur color is generated, size, tail length, activity level, weight, collar color are all generated. And then once all of these properties, their values have been generated, a dog is born. So I said that there are rules that determine these properties. Where are those rules? Well, here is our dog class in Python. So what we do is we have a dog class right over here. And you could see that some of these properties, each property has an associated Python variable. So we have self-genetics, self-nutrition, self-age, and self-sex. You can see that these are determined by random choice. We randomly choose, randomly choose, randomly choose, and we randomly choose. And just so you understand here, genetics is simply from these choices. German Shepherd, Labrador, Bulldog, Beagle, Pug, Rottweiler. So it's one of these values. Nutrition can either be low, medium, or high. Fur color can be any of these colors, black, white, brown, golden. Size can be any of these. Tail length can be any of these. Collar color can be any of these. Weight can be any of these. Activity level sex. So anyway, these are determined like this, properties assigned by random choice, and then there are properties assigned by other properties. So for example, in this case, we look at genetics, and if the genetics is German Shepherd, we assign fur color to be tan, size to be large, tail length to be long, and activity level to be high. But actually, we sometimes reassign variables. For example, if age is less than or equal to 2, what we'll do is we'll reassign the size to be small. It could have been assigned to be large, and the tail length to be short, the activity level to be high. But ultimately, even though, we reassign variables, effectively, we know that size is determined now not only by the genetics, but also by the age as well. Now, one thing here, this is actually not supposed to be here, but we'll look at this later. This is because we have access to the mechanisms, we can actually perform an intervention, meaning we can, for example, activity level is determined by genetics and age. But as God, we can actually disconnect this relationship and force it to be any value we choose. So later we'll come back to this, and we are going to perform an intervention where we're going to force the activity level to be high. And we're going to disconnect genetics and age. And we're going to see the result of that. Okay. So now let us go to our experiment. Now with our experiment, what we're going to do is we want to generate 1,000 dogs, and we want to explore their weights. So I have this dog population object that can generate dogs pretty quickly. You just specify the number of dogs. It'll generate a bunch of dog objects, and then it'll also put it in a pandas data frame. So I've already run this. I ran this here. I used a random seed of 42, and then I created a dog population, and then I created a CSV file. Note that I used this random seed 42 here, meaning that while these variables that don't have any arrows pointing to them, genetics, age, sex, nutrition, were assigned random values, they were assigned random values based on a seed of 42. And later on, when we perform the intervention, we're going to use the same seed. So genetics, age, sex, nutrition are going to be assigned the same random values. Okay. So what I've done here is I've already generated this, what I call natural dog population. I call it natural because it's kind of the values were generated naturally without any intervention. So this is here. And you can see here we have a lot of data. We have genetics, nutrition, age, sex, fur color, and we can see it varies for different dogs. We have a pink collar, blue collar, green collar, red collar, pink color. I think I really like this way of generating data because while there is some randomness, there also is some order. And that order exists because the fact that certain properties are determined by other properties. This would be an interesting way, I think, of generating data. Or even as we're generating dogs, maybe this could be a way of generating different characters in video games. Who knows? Anyway, so we got this natural dog population. This is cool. Let's kind of explore that natural dog population. In particular, I said I want to look at the weight values. So what I'll do is I'm going to comment this out, and I've already written some code here that'll explore the number of dogs, the weights of the dogs. So this is basically um, explore the weights of the dogs. And we run this here. So it loads this natural dogs population.csv, and then we look. So remember, we have 1,000 dogs in our natural dog population, and we can see 467 of them are heavy, 286 are medium, and 247 are light. Cool. Now we're going to perform a divine intervention. We are God in this scenario, so we have full control of the mechanisms that are creating the dogs, so we can force variables to be values. In this case, we are going to force the activity level to be high. Just to reiterate, we are disconnecting this relationship and this relationship, and we're forcing activity level to be high. Now the question is, will the weights change? Let's take a look. Looks like some duplication happened here. So what I've done is similarly for the like how you generate the natural dog population, what I did is I simply made this intervention and then I ran this code here where I regenerated the population of 1,000. Notice that I use the same random seed. And as I discussed before, because I use the same random seed, those variables that are assigned by random number generators are assigned the same random values. So really the only difference between this population and the old population is that there was a divine intervention. Now, we have high activity dog population. This was generated here, and you can see the data as well. We have color pink, weight light, color blue, green, red, pink, weight light, weight. So you can see all of these different values. But the question is, are the weight values going to be different? Intuitively, we would think so. So let's run that. Okay, so the order is kind of reversed here a little bit. We can see for the light dogs, there's actually 389 light dogs and 247 light dogs in the natural dog population. So the number of light dogs actually increased. The number of medium dogs actually decreased, 286 to 277. The number of heavy dogs actually increased as well, 467 to 334. So by forcing all the dogs to be very active, we effectively made the dogs a lot lighter. So this is very curious because this allows us to actually understand what the effect of some sort of intervention is. One other idea I had was, can we predict the results of an intervention without actually even performing the intervention? So if we, for example, look here, we performed the intervention by disconnecting these relationships and then forcing the activity level to be high, and then rerunning the simulation 1,000 times. The question is, can we predict the results of running the simulation without actually running the simulation? And this is also inspired by causal inference, where causal inference allows you to predict the results of an intervention without actually performing the intervention. So in this case, what we could do, which we can do in later code, is just some basic ideas here. is that these rows that have an activity level of high already, they're actually good. Forcing the activity level to be high is not going to change anything because the activity level is already high. The only case is for these cases where the activity level is medium or the activity level is low. In those cases, if we open up the property relationships, if the activity level was actually low, that's going to result in a certain value for the weight. So changing the activity level high will actually change the weight value. So in those cases, what we need to do is we need to look at other rows and examples to see what would the weight value would have been if the activity level was low, or activity level was high, or activity level was medium. So basically using other rows, I think we should be able to figure out what would have happened without actually performing any experiment.